Hey, Dr. Cluck coming back at you here, and in this one we're going to look at surface integrals again, but in this case it's not surface integrals for a function, it's surface integrals where we incorporate a vector field. So imagine you've got like a surface, and on that surface the wind is, say, blowing through it, and you want to know like the flux through that surface, you know, of the wind, or, you know, it's a fishing net and how much water is flowing through it, or it's a magnetic field and you want to know how the magnetic field is interacting with the surface, something like that. So let's jump into it here. So it's still surface integrals, but what we're calling it now would be flux through a surface, okay? And so the vector field F, okay, we're dotting that with the normal vector n, and that creates a quantity of flux. Now really, that once you've done that dot product, you just get some quantity that you're integrating. So it still is a surface integral. It's just that the function, that little f that we're integrating, is coming from a vector field. So we're calling that f dot n here. Okay? Now, once you've got that set up, you might want to know, well, how do you do NDS? We've seen this before when we did line integrals with curves, where we had nd little s, and then we packaged it up into a little quantity, and we're going to get the same thing, where if the surface is some function z equals g of xy, then the package NDS comes from negative gx, negative gy1, dA. This together is equal to that because the stretch factor is contained in this normal vector. So this is not a unit normal vector. This n is a unit normal vector, but this vector here is not a unit vector, and the length of this vector is exactly equal to the stretch factor that dA goes through in order to get to ds. And so nds is equal to this quantity because we've bundled the two units together. Okay? Now, in terms of what you might imagine, how would you apply this? Well, say you had a big, you know, maybe a big cardboard, you know, object, and the wind was blowing against it, and you wanted to quantify, well, how much force is that wind doing on that cardboard object? So, you know, maybe you've got like a big boom box or something. The wind's blowing on it, and it's tipping you over or something. This integral here might quantify the force of the wind, you know, do the flux of that on that cardboard box, something like that. That's kind of how you might imagine it. Okay, and just a quick note, some textbooks don't write the n here for some reason. They just write .ds. I think that's a mistake. It hides what's really going on, but nevertheless, they do write that notation, so keep an eye out if that's your textbook. Okay, so what's going to happen then, all packaged up together, is if you've got a vector field, PQR, right, and you want to know the flux of that vector field through a surface, and we're going to call it either upward or outward, and then it's this would be the definition, and then mathematically it's equal to this. It's PQR dotted with negative gx, negative gy1. Notice this vector 1 here in the z means we're getting an upward vector. If the flux was supposed to be pointing down, then you would just multiply this by -1, so you'd have gx, gy, -1. But generally speaking, up is out, and so this is the right quantity. Okay, so that's the main idea that we're looking at. In the next video, we'll do some examples to see how do you actually compute these problems.